Hello, everyone. So today we are dealing with the week 11 of the course. Okay. Thank you, Manisha, for joining. If you have doubt, you can please just let me know what is your doubt. This is about week 11. Okay. So here, it is about digital communication. Okay, so here we will see some digital communication, their MATLAB codes, and also some analysis using the block diagram and some perspective of this software defined radio. Okay, this particular material I will be uploading there in the drive link. Ah, okay. So basically, what we want is okay. What is our thing is concept review includes sampling, aliasing, reconstruction, low pass filtering, frequency up conversion, and frequency down conversion, and the physical layer model. Okay. So if you see this particular figure displays a digital communication processing chain for both the transmitter and the receiver. Okay. In the 7-layer open systems interconnection model, the physical layer or the layer one defines the means of transmitting raw bits over a physical link. For a digital communication, the chain begins and ends with a binary message. This binary message may represent, for example, speech, audio, or image, or high definition television. Okay, and the transmitter bits are encoded for error protection and converted to a sequence of discrete symbols. Okay, so at the transmitter, it is like this. Okay, the symbols must be converted to a waveform suitable for transmission in a process known as pulse shaping. So that we also saw using a MATLAB uh, exercise. What is the pulse shaping? The bits are encoded for error protection and convert to a sequence of discrete symbols. The symbols must be converted to a waveform because now you have bits that will be converted to a waveform, and again the 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 conversion of symbols to a waveform is known as pulse shaping, where symbols are converted to sample data based message. Then the sample data are converted to an analog voltage signal through a digital to analog converter. Now you have bits, then sequence of bits, then sequence of bits to a pulse shaping, then pulse shaping to digital to analog converter. Okay. This conversion often also entails a frequency shift to an intermediate frequency. So whatever the frequency you will have the shift because of the delay. And the delay is associating the shift in the frequency domain, that intermediate frequency. The intermediate frequency signal is then modulated to a frequency that is matched to a desired transmission signal. So again, it is modulated to a mass desired signal such as license band for commercial radio frequency transmission. So understand this flow. So first of all, we have a device, and in the device, everything is having the 7 layers. The 7-layer open system is having the physical layer, the level one, which defines the means of transmitting raw bits over a physical link. Now, for the digital communication, the chain begins with and ends with a binary message. The binary message may represent any signal. Now, at the transmitter bits are encoded for protection and converted to a sequence of discrete symbols. So, this is all about, I'm talking about the digital communication. So, that's why I'm starting with this. Okay. Now, uh, once it is converted to a pulse shaping, then again it is modulated so that that is matched to a desired transmission signal that is such as license band for the commercial radio frequency transmission. Now we understood this transmission part. Okay, digital to analog. Since it was a digital communication, so it started with digital frequency. Okay, started with digital signals. Now, if we talk about the receiver processing chain, okay, it mirrors the transmission chain, but with added complexity to handle the synchronization of receiver to the transmitter. Since the receiver is there, it should synchronize properly with the transmitter and to accommodate the signal distortions or impairments due to transmission resulting from the thermal noise at the receiver. So basically, what I'm trying to do is you have transmitter, then you have channel, okay, just noise. Then it is passed to a receiver. It will actually mirror everything, Felix, but it will have the added complexities, which we are talking about. Okay. Due to transmission resulting from thermal noise at the receiver. The receiver designed to mitigate this impairments is considered in chapter 5 and 6 that we will take care. I am also taking the extra class on Monday from 6 to 7. This is a 1 hour extra class. Just requesting Manisha, you please join. And if you have any doubt, you can mail me also. Okay, like previous, like you do usually. Okay, so yes. So symbols are illustrated. So first of all, let's see this figure 1. Okay. Physical layer communication processing chain for transmission and reception. So we saw what is transmission. So we are having bits. Okay, you are having bits and two. Is lag due to internet connectivity. Just show this. So block diagram, if we see this is transmission. You're having bits. Through channel encoding, you have sequence of bits. Channel encoding is for using probability of error. Okay, now it will have sequence of bits, then it will map to a symbols. Sequence of bits map by 0, 0 like that. Okay, now after the symbols you're getting, it will convert to a pulse because that pulse will only help for the modulation. Once this pulse is generated, then that is for the digital baseband signal. Now, the digital baseband signal is passed to a digital to analog converter. It will convert to this analog baseband signal. Once the analog baseband signal is there, then after that you have the modulation. What is modulation? Modulation is a way of converting or converting a low frequency signal to high frequency signal through what? Through various type of modulation. It can be amplitude modulation, can be phase modulation, and calm is the mix of phase plus amplitude. Now, that's modulation done. That is called RF signal, and this is called transmission amplifier. Okay, and this is the antenna. This is all about transmission. Now we were talking about the reception also. Okay, the symbols are illustrated in figure 1.2 for the ease of quadrature phase shifting symbol constellation, also known as four array quadrature amplitude modulation. Okay. So in QPSK, pair of bits are mapped to one of the four equal energy symbols. Okay. Pair of bits are mapped to four equal energy symbols. And the decoding of noisy two bits, we will see. Typical impulse response for pulse shaping is illustrated there. We will see the role of pulse shaping filter and necessary design general considered. Moving down to transmission chain. The in-phase channel of a 47-bit baseband message is shown in this one, and the corresponding baseband bandpass signal with acoustic carrier frequency. Okay. Now, if we talk about the software, a radio is a kind of any device that wirelessly transmit or receive signals at the radio frequency. So, radio is nothing but is a device that wirelessly transmit or receive signals at the radio frequency, wavelengths of the electromagnetic spectrum. The radios are found in many products, such as cell phones, tablet computers, automobiles, televisions, spectrometers, and a magnetic resonance imagers. So a software-defined radio can be defined as a radio in which some or all of the physical functions are implemented through modifiable software operating on the programmable source processing technology. Okay. A conventional hardware-based radio device provides operational flexibility only by physically changing the hardware components. In contrast, software-defined radio provides an expensive multi-mode, multi-function, multi-protocol device that can be modified using the software upgrades. So we just saw about the transmission part, but if you want to see about the reception part, so here you have input as a receiver amplifier. Then this is the RF signal. Then this is a COM demodulation. Then this is a COM modulation. Okay. In modulation, you are multiplying it into power j2 pi SCP. In COM demodulation, you are multiplying it with respect to delay. Suppose it you're okay, it's actually the mirrors, but it is opposite. Then you'll have the COM basic. Then you'll have analog to digital convert. When you have analog to digital converter, you have digital baseband signal. When we have digital baseband signal, we want match filtering and the symbol sync because this synchronization is required. Okay. For the successful decoding of the message signal. Because what was transmitted? What was transmitted? Okay. Now you have after this match filtering, you have frame sequence, frequency synchronization, channel equalization. So you will have after match filtering, you'll have this synchronization. Once you have these things, you'll have symbols, symbol mapping back to bits, and finally after channel decoding back to bits, whatever we transmitted. So we started with the bits. Okay. Now we started with the bits and finally we came also to the bits in the reception. But the only added thing is the delay associated while demodulation. This is delta and with the synchronization because we have to just take care of the frame synchronization, pilot sequence, frequency synchronization, and channel equalization. Okay. And match filtering. With all this added functionality, we have the receiver. And as we know, the radio is nothing but a device that receives the signal at particular frequency or wavelength that is specified in the radio frequency. Now, we will see how this is all about the physical layer communication processing chain for transmission and reception that happens in digital communication. And the week 11 was all about that only. We'll see some figures also where we can analyze how actually these things look like. So suppose you have constellation of 4 form. Since this is showing n array, yes, we have 1, 2, 3, 4. 4, okay? N is equals to 4 equals to log 2n. How many bits? Okay, so n, so number of bits is n, and number of bits n. This is 2. So every symbol having 2 bits. Similarly, here you can see 0, 0, 0, 1, 1, 0, 1, 1. Okay, 0, 0, 0, 1, 1, 0, 1, 1. And from here you can write anything. And all these 4 symbols are having same energy. Okay. And this is imaginary part and the real part. Now, pulse shaping filter was required at the transmit. Okay, because once we have the symbols, we want to shape it into pulse so that after modulation, it will go to higher frequency. So this pulse shaping filter, basically, this is the always same function. And you have this baseband signal, and this is a band pass baseband signal without modulation. is a bandpass signal with modulation. So here, basically, after if you, I'll just explain you how this is looking like a two frequency signals. See, you can see here you are having different signals, but in the frequency domain, you can see only two peak frequency. How come? Because in modulation, what actually you're doing, you're just multiplying a signal with the e power j2 pi fct. Again, this is a baseband signal. And finally, you're getting the power modulated or anything based on that. Because if you modify, it can be sine or cosine. So if you have this frequency domain, I'm just talking about the frequency domain, because this you can write some in frequency domain, because this is a baseband signal. So some in frequency domain, this is NT. Okay. Now this is NT. So, and F frequency domain I'm talking about. Once we are multiplied with cosine 2 pi fct, then it will go SL. This is modulated signal. Why? Because cos 2 pi fct is equals to what? This is in time domain. If you do the multiplication sequence of it, so it is 1 by 2 del f minus fc plus f plus fc. Cos have this particular Fourier transform. This is C, this is minus FC. So once this is multiplied, so that is actually the convolution, the frequency domain, and that got shifted to these spectra. Okay, that got shifted to these spectra. So that's why we have this particular form of spectra. Okay, now this is a band pass signal for the 1800 hertz. So if you can see, if suppose it is having some 200 megahertz. So FC plus 200, FC minus 200. So that will be FC 1800, which is 1800 plus 200, which is 2K. So here 2K is there. Okay. It's all about simple things. Okay. Now, if we talk about typical software defined radio architecture. Okay. So you don't have to worry how typical software radio defined radio architecture looks like. But you can see here you will have the antenna and data in, data out, and low noise amplifier, the low pass filter associated with each modulator, and local oscillator, then DDC, digital to converter, DSP, FPGA, and all those things. Analog to digital converter. So digital up conversion numerically next. So if you want to see something, it's a typical SDR architecture is shown as we just saw. For operation at frequencies above ultra high band, the current SDRs use mixers at the front end to perform analog up conversion and down conversion to and from the desired frequency band. On receive, the wireless signal induces the on the antenna a current which is boosted by low noise amplifier. Okay, and filtered before down conversion to in phase and the quadrature channels at an intermediate frequency. The IF frequency signal is then directly sampled by a analog to digital converter, and digital down converters then further down convert the signal via multiplication, which results in signal at the sum and the difference of frequencies. A set of steps on transmission and digital up conversion Numerical index is a baseband signal to an IF frequency. Okay, so digital up conversion and DDC. Okay, the digital mixer, and these are the up conversion baseband processors. This can be baseband processor. So it will be only passing through a digital converter followed by low pass filter. Now, if we go to some again, the previous part, which is because this sampling and aliasing is very, very important for the digital communication that we cannot even ignore that part. Okay. So if you want to see here what actually the sampling and aliasing feels like. Okay. So basic intuition of sampling and aliasing is evident in figure 1.4. So let's see this particular thing. Just give me a second. Net is not right. Okay, so we can see here the illustration of sampling and aliasing. So here we have amplitude and time signals. Okay, and amplitude and time signals. So let's see exactly this means. So basic intuition of sampling and aliasing, given only samples of a sinusoidal waveform, there exists a tones of infinitely many frequencies that pass through the samples. Okay, the frequencies of these possible interpolating waveforms differ by a multiple of the sampling frequency. So in the figure, the solid line shows mt is equal to sine 2 pi 20t, a sine wave at 20 hertz. Solid line. This is sine 2 pi 20t. Sine 2 pi 20t. A sample shown by dot on the sticks are taken every 0.0 seconds for a sampling rate of fs equals to 100 samples per second. So these are the samples taken every dot. Okay. fs equals to 100 samples per second. Okay. Samples per second. So the top panel shows that sine 2 pi 20 plus fst is equals to sine 120t is also consistent with the same set of samples like the bottom figure illustrates that. Oh, this is sine 2 pi 20 minus fst is equals to sine 2 pi minus 80t is equals to another tone getting the same samples. Oh, so here you can see here sine 2 pi 20t plus 2 by FST. Just showing the same sample as fine. 2 by 20t minus 2 by FST or equals to sine 2 by 20t plus some integer multiplication of 2 FST, like that. So what does it shows? So the Fourier spectrum XF of the sample signal contains the sum of these possibilities. So this is xt is equals to mt convolution with delta t minus nt into sample signal. Then so sampling is nothing but it multiplied with del t, and if in the time, if the frequency domain comes, so it is actually the convolution of the frequency domain. And this is what it is shown. When MF is a spectrum of the original signal, MT, and each shifted replica of the spectrum MF in equation 1.1 is called an image. So you remember this thing. To eliminate confusion among the possible signals in a sample waveform, the Nyquist criteria stipulates that MF equals to 0 for all F del F greater than equals to Fs by 2. That is, Nyquist criterion stipulates that the sampling rate yield at least 2 samples per cycle for any frequency present in MT. So here we have to, more generally, a bandpass and sampling of a real valued signal MT requires that a two-sided bandwidth of the spectra MF. Yes, Manish, any doubt? No. It is only for this particular frequency that we are just keeping the limit on F. You can't actually define for all the F. You are try to understand this particular equation. Then you will understand. Equation 1.1. Have at least some understanding. Oh, okay. I'll move ahead. Okay, fine. Now, so in this manner, the areas of MS appears with frequency support confined to minus Fs by 2 to plus Fs by 2. Agree? Hmm? Now, frequency up conversion. Up conversion means amplitude modulation or mixing of a real valued message signal. It is given by MT is equals to cos 2 pi FCT. And it serves to translate the message to a desired frequency band centered on a carrier frequency FC. The up conversion is graphically depicted in this one. Let's see what is the up conversion. The spectra is formed by a Fourier transform. This is this, like, as I already told, what is up conversion? Just a multiplication with this one. This sometimes up conversion is also uh, can be also taught as a amplitude modulation. So here also showing amplitude modulation performs translation the frequency. The magnitude spectrum resulting from the amplitude modulation. So as we know, we all know about this, and this is FC plus W, FC minus W. That's why the bandwidth changes by FC plus W minus FC minus W, and this is 2W. Okay, so amplitude modulation is resulting in bandwidth by W. This is what up conversion rate can be seen. frequency down conversion. With FC, no, a down conversion or amplitude demodulation can be accomplished by mixing and low pass filtering. Okay. Once we are done with this, okay. So we are passing with a low pass filter. And we know the low pass filter will only pass the low frequencies or the DC frequencies. Right. So in this case, do you think that this is given to any low pass frequencies? No, right? Not at all. So it is only given to NT. So amplitude demodulation. You may wonder why this. I told you that because this is having e power j 2 pi fct, now e power minus j 2 pi fct. So this frequency will be associated with the plus and minus of this. So again, this is greater than a baseband frequency. That's it. Low pass filter has a pass band cutoff of greater than W hertz and stop band cutoff of 2fc minus W. Again, why pass band cutoff W hertz? Because that only if you have this empty W, so the B band pass filter should have this cutoff, right? And it should not, okay, minimum is this one, but it should not lead to 2fc minus W because we'll have another spectra as fc. Okay, and this is going to, what is the difference here? What is the space here? So fc minus W. Okay, so B should not be less than or equal to 2fc minus W. Why? Because you are just shifting to 2fc. That's right, 2fc minus W, it should be less than that. Now, if you want to see the time varying attenuation, okay. So time varying attenuation can be viewed as an upconversion of MT to a frequency equal to offset. The estimation and correction of this offset will be considered in several chapter. We'll see that. Okay, time varying attenuation. I don't think that you will have that problem. But again, when a receiver oscillator has the frequency offset F delta or the phase shift offset phi relative to the up conversion and the demodulated signal is Vt is equals to low pass filter mt cos 2 pi fct into 2 cos 2 pi fct plus z. Suppose you're having this as a demodulator at the receiver. This is what at the receiver you'll have because this is modulated output. Again, you are multiplying with a 2 cos something. This is the demodulator output, and you are doing the low pass conversion to have the baseband signal again as an output. But again, if we have this f delta and phi, try to understand how this is coming. Time varying attenuation. Please understand. Give me a second. If you have doubt, please write in the chat box. Understood. This is just a time varying attenuation associated with F delta n phi. For now we will go to interpolation. Interpolation is a digital filtering procedure that increases the sampling rate by integer factor L. So here, suppose you are having this yk is equals to summation of minus n equals to minus infinity to infinity, x is input, and this sine pi k minus nl divided by L divided by pi k minus nl divided by L. So it actually interlacing the L minus 1 zeros between two consecutive samples of x. So you're having the distinct or discrete samples and you're adding zeros. And you may wonder why this interpolation is required. Because we need to increase the sampling rate again. In some cases, to avoid the aliasing, we need to increase the sampling rate. So how can we increase the sampling rate? We have to increase the sampling rate by without disturbing the existing samples, and also we want to increase the sampling rate as we just saw the conversion and some distortion of the amplitude time varying attenuation from the perspective of amplitude modulation. Now, once we have discrete symbols, we need to increase the sampling rate by increasing factor L. So the process is nothing but this one. The block diagram for the ideal interpolation is uh, increasing L, then sparse by a low pass filter, then YK you'll have. Now, digital to analog conversion, the sync interpolation. The ideal digital to analog conversion is implemented by a sync interpolation, which is illustrated in this figure. So let's see. Where T is a sampling period, the summation is the convolution of low pass filter impulse response. That is a scaled sync function with the impulse train of samples. This summation is depicted in the figure where the solid circles denote the sample values, and the dashed lines denotes the each shifted scale sync function. And the summation is shown by the solid line with zero crossing of the sync function, which occurs every t seconds, to ensure the faithful interpolation of the original symbols. So what things see? First of all, we have the summation is depicted in the pair where the solid lines denote the samples minus 2, 2, 4, 4, 2. Minus 2, 2, 4, 4, 2. This is the summation. Oh, sorry. Okay. Summation is a convolution of the low pass filter response. Okay. It's actually a low pass filter response. It means convolution of low pass filter response. A scaled sync function with impulse. Okay, a dash line denotes the each shifted and scaled sync function. So see, first you have this, orange, then this, and finally summation. This is a illustration of sync interpolation, how the interpolation works. So actually, we are trying to increase the sampling rate. Okay, and summation is from a solid one. The zero crossing of the sync function, which occurs every t seconds, ensure the faithful interpolation of the original samples. So every zero crossing is actually matched. See, you're having zero crossing is matched. Now decimation. Decimation is a digital filtering process that increases the sampling rate. Now you will shall tell me, uh, this is summation in the time domain, but if you do in frequency domain, just a convolution. Okay. So don't try to think in a different way. It's a convolution of impulse function just shifted the frequency in that particular frequency. Okay. As we know, xt convolution with then t minus tc is nothing but x t minus tc, right? Similarly, but it is again in frequency domain. Now, decimation is a digital filtering process that decreases the sampling rate. Given an original sample rate of SPS, the decimation by a positive integer L produces a new sampling rate Fs by L. In the interpolation, it was Fs into L, right? In here, it is Fs by L. Decimation. So, so the signal is first low pass filter, typically in stages with the cutoff frequency Fs by 2L. The filtering prevents the aliasing from when the signal is downsampled because here you are just removing the samples. Okay, here you are removing the samples. So you also have the information loss here. Okay. So if only every LH symbol of the filtered output is computed and retained. Okay. This is what the block diagram looks. Exploration. So here in this chapter, a guided set of exploration is presented. Useful commands are introduced and used in example snippets. So I have the code as well. I can just share in the drive link. Okay. So getting started with audio input output. First of all, you have 4 commands allow you to access the sound card hardware from within the MATLAB to record the audio signals. So this particular audio recorder, which is having the Fs as a sampling frequency, a number of bits and a number of channels, sets the sample rate Fs in samples per second, the number of bits per second per sample n bits, and the number of channels. The defaults are Fs equals to 8,000, n bits is equals to 8, and number of channels equals to 1. Now record blocking. It will record the sounds for the length of sounds and does not return the control until the recording completes. Then you'll have get audio data. It creates an array to store the recorded signal values. Okay. And get record object, because here we have just created a record object that only we are using in the function. These are the member functions. It queries the properties of the audio recorder object, direct object. The valid values of the sampling rate depend on the specific audio hardware installed. Suppose the typical values supported by most sound cards are 8,000, 11,000, 25, 22,000, 50, 44,100, 48,000, and 96,000 samples per second. The code snippet in table 1 provides an example. We'll see that. And the typing your own code as you do example exercise will help in building some familiarity. So I just wanted you to just go through that and you can just type these things. Playing audio. Similarly, two audio commands allow a user to play the audio to the sound card within the MATLAB. It will first create an audio object player object. And these are the by default code that is already existing. Okay. So now the classes are already existing in MATLAB. We are creating an object of that. And once the object is used, just like in a class in object-oriented program. And as we know, MATLAB is also an OOPS also follows OOPS concepts. So it just writes a class. It is having the member function and member states. So once it is having the data members and a member function. Data members are already defined the public domain or the private or uh, public or private. It can be anything. So it depends on the member function. So that member function of every class is already defined. In that member function, the class with the class name you can create an object, and with the object you can create we can use some various member function associated with it. So display is actually the member function of the class named audio player. Just try to understand from the perspective of C++. Now, have already seen this. This plot TF, okay, it plots the time domain samples in vector X as assuming that the TS is the sampling interval in seconds, and also plots the Riemann sum approximation of the Fourier transform between the frequencies, these things, minus 1 by 2 TS and 1 by 2 TS hertz. So again, you can just have the configuration where you can have the only time domain signal or only frequency domain signal, but this plot TF, it actually plots the time domain samples vector X. So I just want you to please go through this. You can have the beautiful understanding of this plot TF, you can visualize it. And in various examples I also showed you some plots and all, but still you can just see by yourself in this case. Again, for the low pass filtering, the command line for the function requires syntax. Okay, the FIRLF where H is the impulse response of the length HL, LH, FPB is the fast bed H, and FSP is the stop bed H, and FS is the sampling frequency. The routine computes the least squares fit to ideal magnitude response illustrated in figure 1.2 that we already saw. So we'll see that. So example of FIR low pass filter design using F4. This is a magnitude and phase spectrum. I'll upload this particular document for you, but please try to understand, try to go through some examples. Now we talk about some AM modulation, demodulation, and say also. So frequency down conversion, the role of the low pass filter is to remove the second term, so-called double frequency form. So you have this exercise. Demodulate the signal S constructed in the step up above. View the demodulated signal in both the time and frequency domains. For the low pass filter, select the filter band LH equals to 49. So for this particular thing, you can modify or we can configure these outputs. Okay, these inputs. So basically, in this particular example, chapter, what we saw is basic signals and systems concepts have been reviewed, sampling, alias, and interpolation. Low pass filtering, frequency up conversion, frequency down conversion, and exercises include the recording and the playing of audio and signals. We'll go to the next. This is the course snippet for. This is a course snippet for students. So sorry for the disturbance. This is the course snippet for the audio recording. You can see the audio recorded object. You try to see this, what actually we are doing. Wait for a while. you both of you went through this particular example and I showed you to have your analysis and your way. Okay. And this is the next part. I'm giving you 2 seconds also for that, for the same. Okay, I hope you have seen this. Again, the summary of the some commands. Please have some understanding in your view. Take your time and see this. There are some more functions. I want you to understand and try to visualize. So convolution, path, help, size, cause, I think plot, TF, these are very, very important for you. Okay. So I'm moving to quadrature amplitude modulation, and there are some set of problems from this particular topic in week 11. So we will complete this particular chapter for further understanding. So this chapter 1 reviewed some basic signals and system concepts, and exercise also includes the recording and playing of audio rate signals. And this lesson, the quadrature amplitude modulation, the coherent demodulation, quadrature demodulation are introduced. The complex baseband is presented as a conventional mathematical notation for representing the form signals. Here we build upon introduction in the previous chapter to implement a COM transmitter and a receiver. Okay, so again, some background. We'll start with some background. In coordinated amplitude modulation, the two real valued messages are modulated simultaneously. Again, you understand this? Two real valued messages are modulated simultaneously, resulting in a band pass spectrum that is not the conjugate symmetric about the carrier frequency. Okay, so the modulation exploits the orthogonality of the sine and the cosine functions minus 1 by 2c to 1 by 2c sine 2 pi f c t cos 2 pi f c t dt. The quadrature modulator, okay, you are just modulating with respect to minus 1 by 2 f c. The quadrature modulator is shown in figure 2.1. The modulator has two branches, one for in-phase signal and that modulates the cosine carrier, and the second for the quadrature signal MQT that modulates the sine carrier. The sine wave is 90 degree, 2 pi by 4 radius, phase delayed from the cosine, as we know, giving rise to the name as quadrature. That's why the name is quadrature. Okay, quadrature amplitude modulation. Two real value signals are modulated simultaneously, resulting in a bandpass spectrum that is not a conjugate symmetric about the carrier frequency. The modulation explores the orthogonality of the sine and cosine. The quadrature modulator can be shown in the figure 2.1. So one has in phase, another has the off phase. Okay. The two modulated waveforms can be viewed as I and Q. So this is in phase component. This is quadrature components. ST, this is the modulator. Now, MIT is pass-through oscillator that has two frequencies, two signals, cos 2 pi FCT, sin 2 pi FCT. That will give in phase and that will give off phase. Okay. So first of all, signal is divided by MQT and MIT. Okay, quadrature amplitude modulation. Ideal demodulation is accomplished is shown in figure 2.2. Okay, for the baseband signals MIT and MQT with the one-sided band with W hertz. The low-pass filter, the demodulator has a pass band edge frequency BP greater than or equal to, and that we know that already for this. This RT demodulator, this is demodulator. This is 2 cos 2 pi FCT and the LPF, and it will give the transmitted in phase component and transmitted quadrature component. Okay. Simple trigonometric identities can be used to verify for the RT is equals to ST, that is a noiseless and a distortionless channel. The message signals are perfectly recovered. Okay. Outcome RT is then multiplied with the same oscillator, first NT and QT, then they are added together. Then this is a demodulator. Try to understand this particular. This is a modulator. See for 2 seconds. This is the modulator. Okay. Now for the deep modulator, what you're doing, you're just having RT, that is some part, and then you're multiplying with cos to pi FCT and sin to pi FCT. Again, this is not a simple cos and sin. This is the 2 cos to pi FCT and 2 sin to pi FCT. Okay, then pass to a low pass filter, VIT and VQT. The low pass filtering removes the double frequency component. For the coherent receiver described in equation 2.3, is the coherent receiver. Coherent receiver means that the receiver frequency is same as oscillator. That's why this is covariant. The oscillator, which is generating the frequency, which is FC or 2FC, it should be same. Should not have the phase of the frequency deviation component. Okay. When the oscillators are not synchronized, this results a coupling at the receiver between I and the Q components, as well as the attenuation of the H. As we should know that. Okay. We require the receiver oscillator is perfectly synchronized with respect to transmitter oscillator, that is a frequency FC. And the phase of the sine and the cosine terms at demodulator must exactly match the frequency and the phase at the demodulator. When the oscillators are not synchronized, this is the coupling. So you try to understand what is coupling. Now, complex baseband representation. The use of complex baseband signal representation provides a simplification in writing, analyzing the programming quadrature amplitude modulation waveform. In the complex waveform representation, it will be again I and J component. So try to understand this mathematics. Yes, it's Manisha, you ask me if you have any doubt in this. I will move ahead. So low pass filter again, the remodulation structure MIT equals to pi FCT minus NQT sin 2 pi FCT. And remember that in demodulation, we are multiplying with e power minus 2 pi FCT. Minus is there in demodulation, plus is there with modulation. All set to go? Fine. Now, frequency domain interpretations of the steps in the modulation and demodulation are given by the frequency spectra that we'll observe. Uh, Observe the asymmetry of the city of the passband signals about the carrier. The corresponding asymmetry of the baseband signals magnitude spectrum. Thus, the upper and the lower sidebands are not redundant in contrast to AM. In AM, we had that redundant. That's why we removed this one side lobe, single side lobe, and double side lobe like that. But here it is not a proper symmetric. It's asymmetric. Remember that it is asymmetric. So the reoperation in the modulator denotes the taking real part of the complex value signal and can be interpreted using Fourier transform relation. So real part is equals to 1 by 2 ut plus u star t. Then Fourier transform is nothing but 1 by 2 uf plus u of star minus f. So again, remember the complex part of any signal, if it is converted to a Fourier transform, it is associated minus frequency. Understood? The convenience of the complex baseband representation results in the widespread use of the complex value signal notation for passband signals encountered, for example, in communication, radar, spectroscopy, and the medical imaging. We see the spectra first. So this is a very good diagram. Okay, I'll explain this in a while. First of all, please go through by yourself what is this showing. Then we will see one by one. Do you understand anything? Just the steps. Okay, I'll understand. I'll make you understand. What is showing? This is a COM modulation. Then we are having the real part of only this thing, and this is the modulator. First of all, the frequency domain of MT is MF of this. Okay, once it is shifted after this mod step one, MF. Okay, step two, after shifting, after modulation here. Then finally, the spectra. Okay, spectra will be symmetric. But again, it is not symmetric properly, it is asymmetric with respect to real. So if it is symmetric, it should be like this. Okay, again, you have this as an input here in the receiver. Then you are just multiplying again with this 2 cos 2 pi minus 2 pi FCT. So you'll have this first step, this is passing this is RF, second step this, and finally you're passing to a low pass filter. You're getting third. This is the input that actually transferred. Okay. The HBT, which is the band pass equivalent channel. So this is HF defined for FC minus W, FC plus W, otherwise it is 0. The equivalence is depicted in the middle of the figure, this one, 2.4. Okay, you see that 2.4 in a while. The equivalence is depicted in the middle panel of the figure 1, 2.4 with the proper modulation, demodulation, and commuting the low pass and the channel filters. We arrive to the bottom panel of the figure 2.4, which is known as a complex baseband equivalent model. Okay, the complex baseband channel model is given by. Okay, this one, the model simplifies the representation, implementation, simulation, and analysis of the communication system. Just see this figure. The complex baseband modulation, bandpass equivalent channel, and complex baseband demodulation. Complex baseband equivalent channel model. Coherent demodulation, I'm just skipping that. Again, if it is not a coherent, then I will have the frequency deviation and the phase deviation. But again, we can see the phase error. A time varying phase error, phi plus 2 pi f delta tsk appears at the receiver output at a frequency offset and a phase offset. As just we saw previously also, but how it varies with time, it is just having the linearly. Okay, that is not good for you. Again, it is not good. We'll see some of the examples now. Here is a delay, is 24 samples, which is 1/2 filter, and that is giving you the output as this. You can see the code once. Okay, I hope you understood. Digital hardware is the output. Illustration of delay impaired by the linear phase filter delay. This is the input and the output. You can see the complete shifting. Again, I'm just skipping the basic operation of a quadrature digital up converter is how interpolator, then inverse sync, then finally DAC. So this AD6654 is a mixed signal IF to baseband receiver consisting of 14-bit 92.16 M space analog to digital converter and a multi-channel digital down converter, multi-channel digital down converter. So it has been optimized for wideband standards such as CDMA 2000 UMTS, TD, STDSMA. SCDSM, okay? And this AD, again, for your knowledge only, AD664 is used as a part of radio system that digitally demodulates and filters IF sample signals. The basic operation is abstract in figure 2.8. Okay, so this is a figure 2.8 that we can see. Okay, so answer is let's create and plot exponential signal ST is an example code. How can you plot? Fs equals to 16,000 sampling rate. T is equals to 0 to 1 by Fs to 0.005, 5 milliseconds. S equals to exponential this part. Notice the use of columns to construct a list. Given a three numbers separated by columns, uniformly sampled list is generated by set starting at the first entry, incrementing by the middle entry, and stopping at the greatest number. These are some examples. I will just update. Okay. This is very important for you to understand the summary. Then we'll go to digital modulation as a chapter third. You understand this? The command, the real part, give yourself a time and just understand and try. You can also take a snippet of this or screenshot of this. Okay. Moving ahead to a digital modulation. So in this lesson, we'll review the digital modulation with emphasis on the special cases of binary and quadrature phase key. So BPSK and QPSK will be here, the prime focus. The chapter equips students to implement the initial steps of digital modulation chain depicted in the figure 1.1 that just I started with the receiver chain and the transmitter, the transmission chain, mapping text to bits to symbols. Likewise, the chapter also develops the inversion of these steps in the receiver chain. Okay. So the transmission chain in figure 1.1 depicts a digital modulator that maps the digital information onto an analog waveform suitable for the communication channel. The mapping is typically performed on blocks of log to m binary digits at a time. When the mapping of bits to waveforms is performed without a dependence on the previous transmitted waveform, so then a modulator is memoryless. You can understand the difference of memoryless without a dependence on the transmitted waveform, there is no memory loss. In addition, the superposition principle holds for a mapping of digital sequence to an analog waveform that modulator is linear. Throughout this chapter, we'll consider the class of memoryless linear modulator known as complex pulse amplitude modulation or quadrature amplitude modulation. So these are the class of modulation. Where in COM the bits are mapped to complex symbols which then modulate the pulse symbols. The complex signal can be represented as AN, GTX, T minus NP. Where AN is a sequence of complex parallel symbols, GTX is the pulse shaped waveform. GTX is pulse shaped waveform. And the symbol rate or the baud rate of MT is 1 by T symbols per second. The bit rate is log to m by t bits per second for a constellation of m symbols. So this is what the complex baseband signal before the modulation is. After pulse shaping, once you are having the bits, that is converted to symbols. When symbols are converted to pulse shaping one, then only you can do the modulation. And this is all about modulation. Okay, AN is a sequence of complex value symbols. GTS is a well-shaped waveform. T is a temporal period. And 1 by T is the baud rate, and a bit rate is log to m by T, bits per second for a constellation of m symbols. The pulse shape GTX is normalized to a unit energy. Uh, Design of pulse shaping filter we will consider in the next chapter, but that is not of our scope. We are constrained to digital modulation. Okay. In this chapter, we'll consider the mapping of sequence of bits to a sequence of symbols and the detection of symbol from a noisy received data. That is our main thing. How can we detect the symbols from a noisy received data sample? Okay. Now, uh, four examples symbol constellations are given in figure 3.1. Three constellations shown in figure have points that differ in their phase. A special case of digital coordinate amplitude modulation known as a digital phase modulation or phase shift key. The name key comes, okay, understand this. The distal the three constellation, let's see this three constellation first. PSK, QPSK, and 8PSK and 16KSK. We will see that because that will have the questions from the assignments from this perspective. Okay. So the three constellations shown in figure have points that differ only in their phase. They're the special case of digital quadrature amplitude modulation known as digital phase modulation or phase shifting. The main key comes from a physical operation of the electrical telegram demonstrated by some professor that a Morse code is a variable length binary code in which the letters of the English alphabet are marked with dots and dashes. The constellation for m is equals to 2 is actually the binary shaped key. The graph depicts the modulated signals using the axis corresponding to two orthogonal signals in form GTX cos 2 pi of ct and GTX sin 2 pi of ct, one side and two side. PPSK is the real value constellation and does not utilize the quadrature carrier sin 2 pi of ct. However, the bandwidth efficiency is improved by simultaneously placing the values on the both orthogonal carriers cos pi of ct and sin 2 pi of ct. So for M is equals to 4, the quadrature phase shift key is the resulting constellation, and the QPSK is essentially PPSK for both cosine and sine carriers. You understand this? QPSK, here you have I and Q component in QPSK, and it utilizes sine and cosine carriers both, so it becomes QPSK. But in BPSK, you will have only sine cosine carriers, not sine carriers. Okay. And this figure 3.1 shows the 8 PSK constellation and associated mapping of bits to symbols. Finally, this shows the 16 constellation. The symbols differs both in amplitude. Means quadrature amplitude modulation. So here you'll have both a phase and amplitude difference. So often used, so 64 and this 256 constellation are often used in digital cable television and cable modem applications for high spectral efficiency over low noise channels. So you remember what type of modulation we used in digital cable television and cable modulation. So here I'm showing you, trying to understand what it actually represents. So this is a BPSK, this is a QPSK, and this is 8PSK. So wait, let you know. The angle difference is 180. Here the symbol angle difference is 45 degrees. Okay. Here it's 22.5 degrees. Okay, this is 8PSK. That's it. Each symbol is having 3 bits, not not com. So com is it's varying in amplitude as well as 16 com. So You can see here the difference is, this is the difference, and amplitude also varied. 16 from 1, 2, 3, 4, and the overall symbols is 16. And since log to 16 is 4, so each bit, each symbol is having 4 bits. And 16 form translation is used, for example, IIT standard for digital communication over telephone networks. It's convenient to normalize the constellation so that the M symbols have the unit average energy. Okay. This is a bit assignments. Try to understand this for 2 seconds or 10 seconds. How big assignments are actually done. So for bit assignments of BPSK, we'll have input bit is 1, 0, -1 and 1. Whereas input bits MSB, LSB will have the symbols as 1 plus j by root 2, -1 plus j by root 2, -1 minus j by root 2, 1 minus j by root 2. So here real and imaginary part is important. Now symbol detection. It's very important as far as the receiver is concerned. And the receiver, we must detect the transmitted symbols and recover the associated bits. If we refer to figure 1 that we started with, receiver processing results in data stream model as a noisy sequence of complex value symbols that will be associated with y delta n is equals to a delta n plus w delta n. Okay. So design receiver processing this model is considered a coded receiver. Scatter plot, for example, for how will this looks like based on these assignments. Okay, try to understand the MATLAB version also. You have a number of symbols is 116. Your M is equals to 4 for KPSK and 2 for BPSK. If M equals to 2, then 2 round and 1 n 1 to n minus 1 noiseless I. Okay, you'll have only I in phase component, not an odd phase component. Okay, and if it is 4, then 2 round I plus j 2 round I and 1 plus 1 to n minus 1 and a is equals to a by square root 2. Then EV by n dot is 6. And these are the scatter plot and how it will look like in phase component, out phase component with 160 noisy QPSK symbols. Here we consider symbol detection whereby a decision is made on a symbol by symbol basis in contrast for modulation scheme with a memory with a receiver jointly performs the detection of the entire sequence of symbols. So here we're considering a non-memory less system. So symbol by symbol detection is being considered. And an intuitive symbol detection rule is to map a received noisy symbol to the nearest constellation point. So how we'll do that nearest constellation point? We just have to find the distance. So indeed, for the equally likely symbols and additive white Gaussian noise of equal variance, the nearest symbol criteria minimize the probability of symbol error. So this is also called it minimum distance detector defines the decision region. Each decision region contains those points closest to a given constellation element. Okay. For BPSK, the decision regions are simply the half planes separated by imaginary axis mapped into logical 1 to logical 0 and easily implemented via the inequality test. In low-level software, this test is merely a test on the sign bit. Okay. Similarly, for the QPSK, the decision regions are for the quarters or the complex plane. So it is also known as minimum distance detector or decision regions. Now, bit and the symbol error rates. These are very, very important. Okay. The probability of symbol error rates depends on the signal to noise ratio in the received data stream. Yn is equals to An plus Wn. And this SNR of Wk is given by P divided by N naught into W. So Es by N naught is just a uh, SNR, and P is the receive signal power experienced at Y, and due to amplified gains, channel noise, loss, and the receiver processing. The noise power spectral density is N naught watts per hertz to model primarily the thermal noise in the receiver amplifiers. The ES is energy per symbol, and EB is equals to ES bit energy. ES divided by log 2M because it is again the energy per bit. So thus we have a variance of Y condition on A cent is SNR inverse and not by ES. Okay. Now consider a special case of BPSK, the energy per bit EV is actually ES because log 2 is 1. Right. So for A cap is equals to 1, an error occurs if the real part is less than 0. Now the real part carries the half noise variance, and hence the variance is N naught by 2B. So their distribution is shown in figure 3.3. Try to understand this, what I'm trying to say here. So what I'm trying to say here is the distribution is shown in figure 3.3, figure 3.3, 3.3 is down. The probability of error for BPSK modulation on a binary Gaussian channel. The probability of bit error when transmitting 1 is then the area for the curve yi is less than equals to 0. Okay. Because suppose you have this, and when it is greater than 0, it should be 1. But when occurs when it is less than 0. So if you do that, you will have P of BPSK is Q of root over 2 EB by N naught. Q function is divided QX. Now considering QPSK, probability of bit error rate decreases exponentially in a positive way. You can see here. This is theory versus simulation. We often do this. Consider the next probability of if QPSK in two cases. First, suppose the bandwidth is equals to W equals to P of inverse. Is identical for the QBPSK and the QPSK and fixed energy per symbol 2 EB by N naught. And for this reason, QPSK is said to be more spectrally efficient than BPSK. The worst bit error is evident for the figure 3.1, where we observe that the distance between the nearest QPSK points is only root 2 by 2 compared to the distance 2 for this. So QPSK is more spectrally efficient but if we see in the perspective of the probability of error, what do you think? What is the difference of probability of error or bit error rate for QPSK and BPSK? Basically, it's same. It's same. Okay, but it is more spectrally efficient. In this chapter is done. These are some command inputs to try to understand. coming in a sense. Okay, so I'm just showing some examples or some questions of last year week 11 questions. So just share my screen. Yes. I hope my screen is visible. Can anyone confirm me? I don't know whether my screen is visible or not, but I'm again trying to. So this is like quiz exam assignment 12. Let me open assignment 11. Assignment 12. Sorry. Assignment 12 is again assignment 12. So sorry what is there. I just have to see. Mm, 2023. Assignment 11 and then assignment 11 detailed solution. Oh, so sorry. Assignment 11 questions are not available, but we can see the assignment 12 only. No problem. So let's see the questions. The Rayleigh fading can be modeled as component of the sum of two uncorrelated Gaussian random variables, the radial component of the sum of two correlated Gaussian random variables, and radial component of the sum two uncorrelated Gaussian random variable, and radial component of the sum two correlated exponential. So basically, no exponential. We can only see that it is a Gaussian random variable. But again, if you just divide in phase component and on phase component, then we saw that both components are uncorrelated. So answer is first. Again, if you want to see the answer, the detailed solution, the Rayleigh fading can be modeled the radial component of the sum of two uncorrelated Gaussian random variables. The Rayleigh fading is often used to model the variations in signal strength or the amplitude in wireless communication channels, particularly when there is a no dominant line of sight and the received signal experiences multiple scattering and the reflections. It is typically characterized by the envelope of the signal which follows a Rayleigh distribution. So some amplitude part. The Rayleigh distribution can be modeled as a radial component of the sum of two uncorrelated Gaussian random variables, making option first to the correct choice. And the phase of these complex Gaussian random variables typically the uniform or uniformly distributed. The other options involving the correlated Gaussian or exponential random variable do not accurately represent the characteristics of the Rayleigh fading. Okay. So large scale fading arises in the wireless communication channel due to path loss as a single function of distance is correct. Shadowing by large objects such as building a hill, all of the correct. So all of the above only is the answer. Because it arises due to both of the mentioned factor. Path loss of signal as a function of distance, where the path loss refers to the reduction in the signal power. As a wireless signal travels over distance, it is a fundamental component of large scale fading and it occurs because signal naturally attenuates as they propagate through space. Shadowing by large object. Now, small-scale fading arises due to multipath delay spread or the Doppler spread or the constructive destructive interference of the multipath signal. So answer is multipath delay spread. Small, these are just a view of these things, okay? Where it is having the Gaussian random where the zero means and the means sigma square variance. The answer is first. Complex Gaussian random variable. And the variation in the signal strength is a function of distance in the phase space proportional to 1 by r square, as we know that from the inverse square law. It signifies the received signal risk power decreases with the square of resistance from the transmitter and the signal strength is inversely proportional to the square of the distance. The signal will distort if the transmitter signal bandwidth is greater than multipath channel or the radio channel. So basically, I get confused, but this is a radio channel because the radio channel is actually the channel. Multipath channel is actually made after having the multiple components in the radio channel. That is called multipath channel. The square of the Rayleigh distribution random variable has exponential distribution. Yes, exponential distribution. You can see the actual formula. It's not a problem. The Rayleigh fading is more applicable to model where non-line of sight exists. Okay, line of sight bias standard. The radiation fading is more applicable to line of sight. So answer should be second. Rayleigh fading is typically used in non-line of sight. So these are the questions from week 12. So I hope that Manisha and Ishan, both of you are appearing for the exam and don't worry for if anything goes wrong. You try to understand and try to memorize some sort of equations for suppose the relay channel and in some mathematics part, you'll definitely score well because these are very easy questions. And if I talk about week 11, week 10, we already talked about week 10 and I will upload all these codes in these things so that you can go through exercise chapter 1. So we saw chapter 1, chapter 2, chapter 3, chapter 3 till this chapter 3. In the extra live session which is happening on the Monday, we will see chapter 4 and chapter 5, chapter 11, and we'll see all the remaining things in week 11. Okay. So I hope you all understood this, and if you have any doubt, you can mail me as Manisha used to mail me. So thank you so much for joining. And I'm waiting for 5 more minutes so that if you have any doubt, you can ask me anytime. Questions are good. It's not that tough. But if you want to focus more, to score more, you have to focus more on week 6, 7, 8. That's very important for you. Okay, if you don't have any further doubts, because since this week 11 was very short and only 3 lectures were there, so I tried to complete as much as possible. But still, if you have any doubt, you can just call me on, email me at my official email ID, e21rach01010 at the IITS.ac.in. Thank you so much for joining and just leaving the class.